In this video, we're going to discuss Coulomb's law. It's a law that helps us find the force on test charge due to a single point charge. So Coulomb's force equal K times Q times Q1 divided by R squared. And as you can see in here, F equal, this is simply just K. And K is a constant which equals 9 times 10 to the power of 9 Newton times meter squared divided by Coulomb squared. So this is K. And then we have Q, which is a point charge, and then we have capital Q, which is another point charge, divided by R squared, which is the radius, which is the distance from one radius to the other radius. This is R, or let's say R squared. And this just says a vector. So let's talk about the constant K. Constant K equal 1 over 4 pi epsilon naught. The 4 pi R squares come from, we know, let's say this is a positive charge. So positive Q. This positive Q emits electric field, and it emits electric field in the shape of a sphere. So the area of a sphere is 4 pi R squared, and this is where we get 4 pi and R squared. Okay, that's done. For epsilon naught, or the permittivity of permittivity of vacuum or empty space. So permittivity in like simple terms is just, let's say we have two plates. This plate, let's say it emits an electric field, or let's change the color. Let's say this plate emits an electric field in this side. So this is the electric field of the plate. It's emits electric field in this direction. There is dipoles in here. In this area there is dipoles, and those dipoles emits an electric field in the opposite direction of the plate electric field. So there will be an opposite electric field due to the dipole. And this is what permittivity really is. It's this so permittivity is the property of every medium and material. And so epsilon naught, which is the permittivity of a vacuum, is equal to 8.85 times 10 to the power of negative 12 Coulomb squared divided by Newton per meter squared. So to make everything clear, we need to put the equation into practice. So the example says 3 identical point charge plus Q form an equilateral triangle. Equilateral triangle, we know that it forms a 60-degree angle in all of the sides, and the sides are equal. So they form an equilateral triangle with sides of length S shown. The magnitude of the net force acting on each point, force F, and the potential energy of the system of the charge is U. One of the 3 point charge is then replaced by negative Q, as you can see in here. So we replace this by negative Q, and we know that Q equals to 2 microcoulombs, and the length is 0.02 meters. What is the magnitude of the net force on charge Q? So you want the net force on charge Q. We know that those two will be attractive. So the positive charge will attract the negative charge, and the other positive charge will attract the negative charge. We know those. Let's break things into components. Makes everything easier. So if we block this, we know this one and this one will cancel, and those will add up. So it will be Q will be moving upward due to those two positive charges. This is the first thing that we need to put in count. Second, we need to find the magnitude. So we know the direction. The magnitude, we will use Coulomb's equation. So F equal Q1. Let's say this one Q1 and this one is Q2, and we'll state this as Q3. Q1 times Q3 divided by S, which has been given as 0.02. I won't write the units, but I'm pretty sure everyone knows the unit by now. And if we put that into a calculator, K is 9 times 10 to the power of 9 times Q1 is given by 2 microcoulomb. Q2 is 2 microcoulomb. In the equation, we don't put negative and positive. Everything is positive. In the equation, we're just finding magnitude, not direction. and then divide by 0.02. Don't forget the square. I forgot to write the square in here. And it will give us 90. And it's the same for both because they have the same R and the same Coulomb. So the same, I don't need to do okay, let's do it. So this one for 1 3, and for 2 3, it will be exactly the same, as it's the same charge and it's the same side. And this was Newton and Newton. I know, as I just said, the angle is 60 degrees, and those will cancel out. So I will find the sine of this. So to find y of 1 3, I will do 90 sine 60, and that will give me, let's put that into our calculator, 9 sine 60, it will give me 77.9. And then I will do for y 2 3, it will give me 9 sine 60, exact same answer, 77.9. I will add both of them, so the net force will be 156, let's say, Newton upwards. So this example says we have 12 charges Q are situated at the corner of a regular 12-side polygon. We want to know what is the net force on the test charge Q at the center. So a test charge is always positive. It's just a test charge is here to help us know, let's say if we have a charge in here, negative Q, we want to know how the electric field of it affects, what the force does it apply on any other charge. We'll put a test charge to help us indicate the force of this charge. Either if it's here or here, we just want to know how strong is the force of that charge. And so we will use a test charge. So we have a test charge in here. Test charge is normally a positive charge. It's always a positive charge. And we have charges all over this 12-sided polygon. And because it's a 12-sided, and I'm pretty sure you're by now you can see that it's symmetrical. So if it's symmetrical, its vectors will cancel out. What I mean by that is this electric field, let's say the charge is positive, this electric field will be cancelled out by this electric field. First of all, they're 12 charge Q, they're equally charged. They're equal charge, so let's say the charge Q stands for 2 coulombs. So 2 coulombs in here, 2 coulombs in here. And they are symmetrical. So they will naturally cancel out. And it's the same for this one and this one. Symmetrical, the same magnitude, will cancel out. So what is the net force on charge Q? Because all of those forces will be cancelled out, so the net force on charge Q will be 0 Newton. And this is the net force. As easy as this. So we have 2 identical charge balls hanging from the ceiling by an insulated rope of equal length, L equal 1.5 meter. A charge Q equals 25 microcoulomb is applied to each ball. Then the 2 balls hang at rest and each suspended hoop is at angle 25 with respect to the vertical. What is the mass of the balls? So let's do the 2 balls, and we create a 25 angle from the vertical, and we have 1.5 length, and we have 25 microcoulomb charge. So we want to find the mass, but first of all, let's draw the force diagram. We have the gravity, as always, force of tension. Let's label them. Force of tension, we can break it down into its component. And yeah, this is our force diagram. We can say that Fg equals Ft cosine theta, because this is theta, opposite is sine, and this one is cosine, so cosine theta. And we can say that, yeah, and don't forget, we have a force of Coulomb in here, and we can say that force of Coulomb equals Ft sine theta. We want to find the mass, but let's see what we have. We have the charge, we have the length. From the length I can find the R. I'm pretty sure I have everything that I need. Things are simple in here. So q squared divided by r squared equal ft sine theta. So I can't find ft, so I can if I found ft, which is the force of tension, it will be really easy for me to find the mass. So because fg cosine theta equals ft, and if I just divide it by sine theta in here, r squared sine theta, I'll be left by that. And yeah, so we know that k is a constant, so it's 9 times 10 to the power of 9. Q has been given 25 times 10 to the power of negative 6 squared. R, easy to find by using trigonometry, and we know that 1.5 sine 25, 1.5 is L, sine opposite 25 is the angle, which would give me, using my calculator, 1.5 sine 25, 0.63, and then I will times it by 2 because I want the total R, which would give me 1.3. So this is R. So R is 1.3 squared sine 25. This is this. And that would give us 9 times 25 times negatives. Sine 25. That will give us a value of 7.8 Newton. And we can use it in here. Okay, why did I divide it by cosine? Cosine theta divided by g to find the mass. And that would give me a value of m equal, we found ft 7.8 Newton, and then cosine, 25, g 9.81 meter per second squared, and that would give me an answer of 0.73 kg for both the balls. That's all. A positive charge Q1 equals, so we have a positive charge Q1, which is 1 microcoulomb, is fixed at the origin, and a second charge Q2 equals negative 2 microcoulomb is fixed at x equal 10 centimeter, so 0.1 meters. Where along the x should a third charge be positioned so that it expresses no force? So let's say this is Q1, 2, and Q3. And we want to place Q3 in a point that there aren't any force on it. So we can say that F1, force of 1 on 3 minus a force of 2 on 3 should always equal 0, because we want a third charge to be positioned so no force acts on it. And that is true to say that F force of 1 on 3 should equal force 2 on 3. And so KQ1 times KQ3 divided by R squared, let's say R squared naught, just to distinguish between the two R's, KQ2 times Q3 divided by R squared. I will cancel KK, cancel Q3, will be left by Q1 divided by R naught squared equal Q2 divided by R squared. This is this. And now we need to know where should we position Q3. Where should it be so there won't be any force acting on it? We can't place it anywhere here because the force in here is really strong. By the electric field is really strong in here, and so I can't place it in here. I need to place it near the smallest charge, which has already been given for us, And so I can write it as Q1 divided by X, which is the distance in here. This one I will state it to be X, equals Q2 squared. Q2 divided by X plus X1. Let's state this as X1. So this is X plus X1 would give us the charge for Q2, the distance for Q2. This is all being squared. To make things easier, so I don't use quadratic formula, I will square things, square root stuff, which would give me square root Q1 divided by X equals square root of Q2 divided by X plus X1. Things are easier this way. Now we will substitute, which is square root of 1 times 10 to the power of negative 6 divided by X equals square root of 2 times 10 power of negative 6. I didn't put negative because we know in Coulomb's equation it's all about magnitude, not direction, divided by X plus 0.1. And then I would do cross multiplication, so it will be square root of 1 times 10 power of negative 6 X plus square root of 1 times 10 power of negative 6 times 0.1, which would give me an answer of 1 times 10 to the power of negative 4 equals square root of 2 times 10 power of negative 6 X. And now I will minus this, so I put this on the other side. 1 times 10 to the power of negative 4 equals square root of 2 times negative 6 times negative 6 minus square root of 1 times negative 6. And that will give me a value of 4.14 times 10 to the power of negative 4x. I will divide this. So divide this by 4.14 times 10 power of negative 4 to find x. So 1 times 10 power of negative 4 divided by the answer, and x should equal 0.24 meters. So we have a charge Q1, which is at the origin, and we have charge Q2, which is negative 1.8 times 10 power negative 8 at the x-axis. We have charge Q3, 2.0 times 10 power of negative 8 at the y-axis, and we want to find, as it says, as shown in the figure, determine the net electrostatic force, magnitude, and direction on charge Q3. So we want to know the magnitude and direction of the force on charge Q3. We know that the force of Q1 on Q3 would be repulsion, as they had the same charge, but at Q3 and Q1 the force will be attraction force. So Q3, Q2, Q3. So let's write the magnitude of those two forces. So force of Q1 on Q3 will be 9 times 10 power of 9 times Q1, which is 1.4 times 10 power of negative 8, times Q3, which is 2.1 times 10 power of negative 8, divided by R, which is 0.24 squared. And that would give us, let's put that into a calculator. That will give us a value of 4.6 times 10 power of negative 5 Newton. And so let's do the same for charge of Q2 on Q3. And that would give us 9 times 10 power of 9, which is K, times Q1, which is Q2, which is 1.8 times 10 power of negative 8. We know in the Coulomb's equation we are just finding magnitude, not direction, so that's why we aren't including the negative, times Q3, which is 2.1 times 10 to the power of negative 8. And that's all divided by the radius. In this case, the radius isn't given directly, as it's been given for force of 1 on 3. The radius, we're going to find it by using Pythagoras, because this is the radius that I'm talking about. And it's simple as doing square root of 0.24 squared plus 0.18 squared. And then all of that's been squared. So it'll be 0.24 squared plus 0.18 squared. And that would give us a value of 3.78 times 10 to the power of negative 5 Newton. So let's draw the diagram. So we have a force in here which is F13, which is 4.6 times 10 power of negative 5 Newton. We have a force downward, which can be broken down into components. And we can use this angle, but we need to first find the angle. I'm pretty sure this is a right triangle. So yeah. And this force equals 3.78 times 10 power of negative 5 Newton. So how to find the angle is by using, we can use different ways really. Let's use the simplest one. I can use sine theta of, let's say, I do have multiple ways. I'm just thinking about the easiest one. Well, to find, let's say, this one, I need the hypotenuse. Let me find the hypotenuse first. So we know the hypotenuse by using Pythagoras would give us 0.3, and 0.3 sine theta would give me 0.18, which is this. And then I will do 0.18 divided by 0.3 sine inverse. That will give me a value of 36.9, let's say, theta. So this is 36.9 theta, and yeah, it's easy. So let's find the force at the y and the force at the x. So the force at the y would do 3.78 times 10 power of negative 5 cosine on the y, 36.9, which would give me a value of 3.02 times 10 power of negative 5. And then if I want the x-axis, I would use sine, and it will give me a value of 2.3 times 10 power of negative 5. And so I will do 4.6 times 10 power of negative 5 minus, which is this number, minus this number, 3.02 times 10 power of negative 5. So the force on the y-axis will be 4.6 times 10 power of negative 5 minus 3.02 times 10 power of negative 5, which would give me a value of 1.58 times 10 power of negative 5. And the force on the x-axis, we have already found it, which is Fx equals 2.3 times 10 power of negative 5 Newton. And now we would use Pythagoras to find the net charge, which is square root of 1.58 times 10 power of negative 5 squared plus 2.3 times 10 power of negative 5 squared. And that F net, let's say, equals 2.8 times 10 power of negative 5. Or this is approximately Newton. So this is the net force, and we found the angle, this angle, or the sorry. We need to find the angle. We found the angle of the triangle, but we need to find the angle of the force. And how to do that? Let me get some space. Okay, that's good. How to do that? We know that the y is 1.58 times 10 power of negative 5 Newton. We know that the x is 2.3 times 10 power of negative 5. Okay, I've drawn the arrows incorrectly. I drew the, okay, wait, just a sec. Because I didn't do the triangle correctly. It should be upward 1.58 times 10 power of negative 5. Toward the right 2.3 times 10 power of negative 5. And this way, which is 2.8 times 10 power of negative 5. You want to know this angle. And that angle would be tan inverse of this divided by this. So 1.58 times 10 power of negative 5 divided by 2.3 times 10 power of negative 5. And that would give me a value of 34.5 approximately degree. And that's all. We found the direction of the force and we found the net force. And thank you for choosing my video, and I hope you gained something.